So moving forward, we have our next talk from Shri Ashutosh Agarwal. Ashutosh Agarwal is currently a principal engineer in the modern system group Qualcomm India. Bangalore, he has been with Qualcomm for the past 8 years with the leadership positions in system design for a number of flagship Qualcomm models. He has past stints with Broadcom India, their WLAN modern systems group and Equinix Communications in their next generation modern design team. Ashutosh has a master's degree in communications from IIT. With this, I would like to invite Shri Ashutosh Agarwal for this delivering the talk.
Yeah, uh, I'm audible, right? Okay. First of all, greetings, Professor Chaturvedi, on your birthday, and thanks, IIT Kanpur for inviting me. We heard Professor Choklingam talk about OTFS, right? And that I'll probably try to do a more bird's eye view, right? At probably an 80,000 feet level, right? And I'll cover a lot of different enablers, roadmap to 6G, and I guess a lot of you would actually have heard of these enablers in one form or the other, right? So the idea would be here that I'll have the slides, but what I'll try to do is to give some perspective of engineers, right, as to how you actually implement, right, and what kind of use cases actually these things go into, and how do we actually see these making impact on the final use cases, right? So that would be the overall gist of the talk. Just a quick look at how 5G is going, because we are going to talk about how 6G is going to look like. 5G has been accelerating globally quite a bit. This is a little bit of an older study, but as you can see, right, 5G has actually accelerated quite a bit fast, right? I mean, actually, you can see 1 billion plus connections in all the way to, I mean, already by 2023. That's actually 2 years faster than 4G, right? So that gives us motivation to actually look at the next generation as well, right? All of these numbers are in billions, so quite fast ramp up on 5G. Okay. A quick timeline on how 6G is going to look like in the specifications, right? So we are actually at release 19 and release 20 would start happening this year, right? So by the end of the year, we'll have release 19 coming out. Release 17 is what we had 5G, and then we had 5G Advanced, which was the second wave of 5G innovations, right? And then we'll enter the 6G age, right? So the idea would be, how do we get from this 5G Advanced, right, where a lot of stuff happened in 5G Advanced, Giga MIMO happened in 5G Advanced, some of the lower IoT stuff happened in 5G Advanced. How do we go from 5G Advanced to 6G, and what would be those drivers be? Okay, so these are the key long-term research vectors, right, that would enable the path towards 6G. AI native A2A communications, I think Professor Choklingam already talked about that. As classically trained engineers, communication engineers, we always look at classical algorithms, right? We'll look at maximum likelihood, we'll look at MMSE. We'll try to fix everything in a very well-defined modeling framework. But as we move forward, I think a lot of the algorithms will be data-driven, right? Network design, even the state side, the UE side design, joint training, model sharing, distributed inference across. I'll talk a little bit more about that, right? Obviously, every time we go from one generation of the spec to the next generation, right, we enable, I mean, bandwidth is any communication engineer's best friend, right? We get linear improvement in capacity with bandwidth. So obviously, we enable more bands, right? We had sub-6 and millimeter wave in 5G. We'll go expand to terahertz, right? And also mid-high band would get enabled. One of the key use cases or key aspirations, right, as we move forward, will be the merging of worlds, right? What we would like to see is that the physical, digital, and the virtual worlds all come together, right? I mean, as you could see, right, as with the invent of AI, a lot of the human interactions that we have with mobile phones today are likely go on to make happen through wearable, right? You'll have XR glasses, you'll probably have other screens that would probably pop up in front of you. So a lot of those transformative, I mean, you'd actually not need to type a lot of things in, right? You'll probably talk about it, you will ask a question to the glass, or you will talk, I mean, and then those inferences would happen on the cloud, right? So what would happen is that the whole interface as to how you interact with, or how you interact with information is actually, right, we type in today and we interact with the laptops. All of that is going to change drastically, right? Because, I mean, with LLMs coming in, you'll actually be able to translate all of your audio questions very, very seamlessly. So merging of worlds is a big, big aspiration as we go forward to 6G. Scalable network architecture, disaggregation, RAN, ORAN. Right? I don't know how many of you have heard of ORAN. Today, network operators actually, or infrastructure vendors give end-to-end solutions. The idea would be to disaggregate all of this so that you can have well-defined APIs where multiple people can come together and integrate this thing. And the topologies, right? We already have coordinated beamforming in 5G, but there'll be a lot of research in terms of how do you deploy networks such that you can scale capacity. So that's going to be another aspiration. Air interface innovations, I think we already heard about OTFS, but typically anytime we move from one generation to the next, we always see quite a bit of interest in how do we improve the air interface, right? How do we make multiplexing better? How do we make modulation better? How do we handle higher Dopplers, delays? All of that goes into the air interface. Obviously, MIMO is a key part of it, right? And that has been one key area that has gone from 4G to 5G to, and that will continue to be a part of 6G. Communications resiliency, I think we'll also have a panel discussion on this. How do we go from, once we have post-quantum, how do we secure these networks, make them robust, tolerant to failures and attacks? So these are the key vectors, right? All of these are very, very rich and very significantly complex. But just to highlight and summarize what are the key aspects, at least, right, from a lower layer, physical layer, which a lot of you might be interested in. How would that, what would the vectors that would look like? Okay, so I put AI ML first up because attention is is what we need, right? So that's what we have here. Yeah, so there are three different phases as we see it, right? So what we have today, and again, I'm talking about primarily lower or mid layers in the communication stack, right? What we have today is this, right? The overlay AI ML, where the on-device, the device, and the networks are actually doing no collaboration, right? So we already have algorithms, use cases, which run independently on each of these networks, right? So the device runs their own algorithms, the network runs their its own algorithms, right? And essentially there is no collaboration. So this is where we are today, right? 5G advanced, already in the spec we have study items, right, which will introduce collaboration between the network and the, obviously, right, when you have collaboration between the network and the UE, you can obviously get a lot more performance enhancement. So this is what is going to happen in 5G advanced release 19, release 20. And I'll talk a little bit about this as I go to the next slides, right? So the difference between this and this is going to be how do you actually look at what kind of collaboration do you have? How do you exchange data between the network and the device to improve learning, right? So that's going to be the next, in the forthcoming years. And then as we go to 6G, right, this is going to be, this is more a philosophical aspect right now, right? So what we are going to talk about is, it operates autonomously across all the layers, right? So you would have across the stack, AI ML working across both devices, and all of this working seamlessly, right? So that's going to be, so this is not very tangible at this point in time, right? But it is going to become all pervasive, right? So that's what I wanted to say. A little bit of color on what are the kind of use cases that we actually, I get this question quite a bit, right, as to what kind of use cases, as I said, right, as traditionally, classically trained communication engineers, we try to model everything, right, and then we try to parameterize it and try to figure out what kind of model fits best for a particular problem. So what kind of issues or what kind of problems do we look at for AI ML today, right? So these are problems that typically are not very well defined, right? One of the problems can be handover, right, for mobility. So you actually see when you go across networks, you may see that thresholds are different, the networks operate, they do handovers at various different times, right? And then there may be a lot of ping pong, right? You may be moving from one base station to the other and then back and forth. So how do you do some kind of learning where the UE and the station can actually measure some of those things and personalize based on where the location is, right? Learn some of these things and avoid those kinds of ping pong handovers. So that's one very, very relevant problem that we're trying to tackle. The other is CSF feedback, right? So, and that's also an item of study in the release 19 and 20, where you typically measure CSI on pilot signals, right? And you send feedback to the network in terms of what MCS modulation coding you would want to use to optimize capacity. But typically what happens is, depending on the deployment, you are actually going to get interference on the pilots or not, right? And the interference may not be impacting your data, right? So how do you actually use learning techniques to ensure that the feedback that you're providing to the network is actually accurate, right? So what may happen is, as I said, your CSIRS, which is the pilot signal, may not be impacted by, or may be impacted by a neighbor cell, right? But you may not get that interference on your data, right? So how do you actually make sure that this discrepancy between your measurements and what you are actually getting is avoided? So that's another very, very typical use case that we are trying to handle here, right? And that, as I said, CSI is also a key use case that has been discussed in the 5G advanced release 1920 studies. Okay, just another mention here, right? So one key thing personally that I think is what AI/ML is going to do is to actually personalize your experiences, right? So that's going to be the major thing. So a lot of our algorithms today, right, are modeled across statistically, right? You talk about MMSE or you talk about anything. So you have a limited number of channels that you're tolerant to, right? What AI/ML is going to do, especially with algorithms like, I mean, you do reinforcement learnings and things like that. A lot of your algorithms that run on your device would actually get personalized, right? So what would happen is your device would actually start learning where you are, when do you actually go to office, when do you go to the gym, right? And what path, for example, which a lot of you might have observed that you go on a certain path day in, day out, and there are dead spots in that path, right? And there is no real way for you to actually handle it. So those kinds of personalization, right, where a particular user is taking a particular path or going to a certain place on a day-to-day basis, how do you improve his performance, right, on top of what is kind of statistically trained? So so on-device training, right, is going to be a major impact. So typically right now what we have, all the training that we do happens offline, right? We actually train models offline and then put them on the device. As we go forward, these models would actually become, I mean, they'll start off somewhere and then you'll actually start training them on device to personalize experiences. Okay, a quick look at the use cases that we have for different AI/ML, right? So one of this is CSI, as I said. So CSI compression is one use case that is being discussed in release 1920. So what we want to do is to actually minimize the overhead in terms of what kind of feedback that you are giving. So that's the CSI feedback case. There is a beam prediction use case where you can do a spatiotemporal beam prediction. This is an FR2 use case where you can actually predict what beam would be the best for the transmitter as well as the receiver to minimize your latency as well as power, right? So that's the other use case. In terms of other use cases, there are also optimized network planning, right? Because different topologies deliver different performance cost trade-offs for GNOBs, IABs, and repeaters, right? So that's one use case primarily on the network side. And then on the air interface design, I talked about CSF overhead reduction. So this is a key use case. Then beam management, right? So I've shown some results. So I mean, with ML, you can actually see the diagonal elements here, right, where the beam prediction is giving quite good performance there. Also, right, and there is a lot of work that is happening on enhanced precise positioning, right? For cases like you have these autonomous guided vehicles, right, and other positioning. So you want to do these positionings and you want to fuse a lot of observations that you might have. You may have observations with GNSS, you may have observations with multi-RTT, AOA, right? A lot of positioning techniques are in place. How do you combine or how do you fuse these techniques, right, to get better and better accuracy? So that's the other area of research that's going on. Okay, yeah, moving on, as I said, obviously as we move on from any one spec to the other, we are going to enable more and more bands, right? So we had millimeter bands and the up all the way up to 7 gigahertz in 5G. What we'll also do is that we'll try to see if we can enable sub-terahertz band, right, above 100 gigahertz and this mid band. So this is one of the crucial think that is going to open up, right? The upper mid band, 7 gigahertz to 24 gigahertz. So this is essentially the key, one of the key research areas in terms of how do we get between these millimeter bands and the sub gigahertz band, right? So obviously there'll also be quite a bit of work in terms of licensed spectrum, which is what we have today, but also unlicensed spectrum, right? NRU was one such study, but this will continue. And shared spectrum. So how do we coexist spectrum between, let's say, when you transition from 6G to 5G, or rather 5G to 6G, then how do you share that spectrum? We today have dynamic spectrum sharing between 5G and 4G. How are you going to share spectrum between 6G and 5G? So that's also going to be an important aspect. Okay, so as I talked about it, the new upper mid bands bring an order of magnitude more wide area capacity. The key part of this is that this is actually the best of both the worlds, right? We have wide area coverage, that is the hallmark of sub 7 gigahertz, and we have wideband capacity as well, right? So we actually get quite a bit of bandwidth here, and we also get quite a bit of coverage. So millimeter wave obviously suffered from lower area, lower coverage. It had quite a bit of bandwidth. So this is kind of the best of both the worlds. So the idea is to actually start supporting quite a bit of new use cases, right? We can obviously deliver new capacity. Boundless XR is another very, very significant use case. We talked about sensing in the previous talk as well, right? So supporting high resolution RF sensing. As we go up in the bandwidth, the band that we are working in, you can actually improve the resolution of sensing, right? So environmental monitoring, activity detection. So all of these significant use cases will be enabled by upper mid band. One of the key other advantages is that you actually have the opportunity to co-site all of these base stations along with the sub 7 gigahertz, right? So unlike millimeter wave, where you actually need to have separate deployments for millimeter wave, these sites that you already have established can be reused for these upper mid bands. Okay. Yeah, a quick look at some things that Qualcomm has been doing, right? So GigaMIMO is going to be something that's going to be, the number of ports that we are going to excite, right, and as we go forward are going to increase substantially, right? So we probably, in most 5G deployments, we probably don't go above 32 CSIS ports, right? We will certainly go significantly higher than that. So obviously the advantage is that once you go to these bands, right, you can, for the same aperture size, you can actually have quite a large number of elements, right? So with this kind of large elements, right, you can see here, right, the green actually shows the coverage that you have, and you can see that for these bands with a higher number of elements, you're actually able to get almost the same coverage as a 256 elements at sub 6 gigahertz at 10 gigahertz, right? So essentially couple the reduction in the wavelength to increase the amount of MIMO that you can do and get more coverage while actually getting more bandwidth. So that's the key part for these bands. Okay, and then we go even higher, right? We make sub terahertz above 100 gigahertz. But this is quite interesting in the sense that obviously, the capacity for these systems is going to be gigantic, right? You're actually going to get in order of 10 gigabits per second and all, right? So the point here is that a lot of use cases that are today wired, right? AI data center is very, very useful, right? A lot of companies make a lot of money in this area, but all of this is wired today. So how do you actually make sure that some of these additional bandwidths can replace these wired, especially some of these wired scenarios into wireless, right? So that's obviously one very strong use case, and ultra precise positioning, right? RF sensing, all of these. The main issues are going to be propagation loss, right? As we go above 100 gigahertz, how are we going to take care of loss, penetration loss, foliage loss, and other, right? So channel modeling, right, in terms of handling, how do you change our MIMO systems to handle these sub terahertz frequency is going to be a key area of research. Also, given that the RF design for these systems is going to be pretty complicated, right? It's actually going to consume a lot of power. So that is also going to be a key area of research in terms of how you can make this happen on a commercial device, right? Millimeter wave actually took quite a bit of time to stabilize, primarily because we did not really have, the systems were pretty complicated, and to put it on a handheld device took quite a bit of effort, and that's going to increase significantly if you go to terahertz. So that's how do you actually fit in a large MIMO system on a small handheld device while keeping power in check, right? So that's going to be the challenge. Okay. Yeah, these are some measurements, right? So we have some research already happening in terms of trying to put these antenna patterns on a device, implementation challenges, right? And also some channel modeling, right? To see what kind of propagation loss exponent that you see. Right? So that's going to be very important, especially if you go to NLOS kind of profiles. You can see that your the loss exponent is going to increase quite significantly as you go above gigahertz, right? I mean, as you increase the frequency. So how do you, I mean, make sure that you have good channel models that get you to the simulation phase, right? And also in parallel try to design the RF part of it. Okay, and then yeah, I mean, capacity is obviously one of the key aspects, right? We obviously every time we design a new spec, we want to get to the capacity of the cellular systems, right? A representative graph as to where we are, right? We at LTE was about 1 Gbps, LTE advanced, in few Gbps. As we go to 5G advanced and 6G, we will start looking at in excess of 10 Gbps throughputs, right? In terms of the total envelope that you can support. So that's unthinkable from the time of 2G, 3G, where we are talking about a few kbps, right? So we are already talking about 10 Gbps throughput on 5G advanced. We'll expand that quite a bit. What I wanted to highlight from an engineering perspective, right, is I think we also mentioned it, is that as we grow all of this throughput, right, I mean, this is quite obvious. We increase the amount of bandwidth that we have, we increase the MIMO capacities, we increase the number of antenna ports. What is going to be very interesting to see is how do we maintain, I mean, we'll probably break Moore's law pretty soon, right? I mean, at least that's the consensus in most quarters. We are already at 3 nanometer nodes, right? I don't think, I'm not really sure how far we can go. So till now, I mean, what's happened is that we have started putting more and more signal processing into our devices. And we have because the nodes have shrunk, we have not really, I mean, we have actually been able to do it, because as you shrink the node, the amount of power that you consume also goes down. The amount of area that you take also goes down, right? So you're still able to fit that in a phone. Now, as you go higher and you're not able to do that, how do you fit a lot of these signal processing algorithms, a lot of this area that you build up into a phone, right? So into a hand, and more precisely into a wearable device, right? A lot of these may need to be fitted into a glass, right? How do you do that? So a lot of focus is actually going to be explore capacity approaching designs, targeting better performance and complexity trade-offs. So how do you keep area, power? So these three dimensions, when we engineer a product, we are always looking at performance, but how do you compensate if you are going to, so it's not just bits per second per hertz. What we look at, bits per second per hertz, per micrometer square, per joule, right? So how do you look at all of these three dimensions, and what is the sweet point, right? Would it actually sell if you increase the throughput to 10 Gbps, but you have a big phone? Is somebody going to buy it, right? So those are the kinds of questions that actually will start monitoring, so or rather mattering. So a lot of research would actually happen. I mean, one good example that I would say, right, as we found out, we went from turbo codes to LDPC codes in 5G, right? Primarily because LDPC codes, the area scales or the throughput scales much better as you go higher in throughput. Right? But the problem is that to gain performance, we have very large code block sizes, right? But once you have very large code block sizes, it takes up a lot of memory. Now, if it takes up a lot of memory to gain that performance, you have to have that area on the phone. Now, if I want to use the same spec for a wearable device like this, I don't have the space. I cannot really do that, right? So how do you scale? How do you tire up and down various kinds of devices, right? And while not giving up a lot of performance. Today, for the same LDPC code, if I reduce my code block size, right, my performance degrades quite a bit, right? I give up 2 dB of performance. Now, people may or may not be ready to take it, right? So how do you make these trade-offs is going to be a very, very strong area of research. So if people, I mean, not just as I again, right, summarize, not just looking at performance, but looking at what's going to cost, right, from a product perspective, if you want to deploy it, both in terms of power as well as in terms of cost. So yeah, so that's going to be an interesting thing to see. Yeah, so I think all of us I mean, we have talked about all of this quite a bit, right? Channel coding, waveform modulation, all of these 3 dimensions are going to be looked at. Multiple access is one key area, right? I mean, full duplex has been the holy grail of communication systems for a long time, right? So we'll try to see how do we actually, I mean, it's been a topic of research for a long time now, but it has never really been deployed. So I think 6G is where we'll again take a stab at it and see if actually we can go to full duplex. And then how do you bridge the gap between, let's say, wireless LAN devices versus wireless WAN? Today, cellular devices are more controlled in the sense you have slotting, you schedule every slot, right? While wireless LAN devices are actually contention based, right? So you actually have trade-off between the two. So how do you bridge that gap in terms of doing contention based access versus slotted access, right? So that's also going to be one of the areas that people would look at. Some of the other areas, right? So advanced RF and baseband joint design. So a lot of work also gets done in terms of how do you trade off performance between, typically people think of RF design as a separate aspect versus baseband design as a separate aspect. There's a lot of work that goes on into how do you actually do joint design, right? So how do you, I mean, for example, if you want to reduce, I mean, a lot of you might be aware of pre-distortion, right? The PA, when you transmit out a signal like OFDM, there's quite a bit of distortion that happens. Now you have digital techniques like digital pre-distortion to actually get rid of that, to reduce the amount of power that, or the cost or the power that the PA will consume. So a lot of those kinds of techniques, right? How do you do co-design, right? You cannot, I mean, as you go to 6G with the amount of bandwidth, right, and the spectrum aggregation that you'll have, you will need to do joint design between RF and baseband, right? These are not going to be independent. Efficient modem system implementations in terms of higher data envelopes, advanced air, and I think we already talked about this. Extreme energy efficient devices and enabling immersive experience, right? Again, the same thing that I highlighted, right? See, in a lot of cases, I mean, we try to improve throughput, right? And then people ask, what's the use of that throughput, right? We are getting 10 Gbps, why do I need 10 Gbps on my phone? And one of the use cases, obviously, right? I mean, if you have capacity, it's not just for that throughput. You can actually get that capacity and then go to sleep, right? So that obviously improves your overall experience. But the problem is that there are a lot of applications, and these applications will increase multifold once you go to XR kind of applications where you have periodic data, right? You don't really, you are getting periodic data, very sparse data, but very small data, right? And how do you take care of that kind of data, both in terms of power, right? Today, if you want to deploy, for example, just to give an example, I mean, if you have a glass today, and if you operate it on cellular, right? If you want to operate a cellular and smart glass on a cellular network, right? You want to run an AI use case versus you want to run that on a WLAN use case, right? The power numbers are significantly different, right? So that's essentially again going back to how do you, I mean, how do you actually take care of multiple users? So how do you design the air interface? How do you design the multiplexing so that you can handle these very different use cases, right? One use case where you have periodic data coming in, but very sparse data coming in. The other is best effort traffic, where you can wait, right? And you can club it all together, right? And then transmit at one go. So those kinds of challenges and trade-offs is what would also be interesting to see. I mean, 5G was supposed to handle it, but to be fair, right? I mean, a lot of those challenges still remain, right? You optimize for one and you always give up something on the other end. So yeah. Multi-rack connectivity is also going to be important, right? So, I mean, obviously 5G, 4G has not gone away. Similarly, when we have 6G, 5G will not go away. So we'll likely have 4G, 5G, 6G. Probably 4G will go away when 6G comes around, but we'll still have 5G. How do you actually take care of this? I mean, the same spectrum, how do you share spectrum? Right? Today we have mobility handovers between 5G and 6G. So that also will be an area of research. Yeah, just wanted to quickly look at this full duplex, right? So as I said, full duplex is the holy grail. We typically have the static TDD here, right, which is deployed right now. And this is what we are looking at, right? The subband full duplex transmission, where you actually have the network or the genome being in full duplex mode, right? While the station or the UEs are actually in half duplex mode. So what this means is that you are actually doing so this is not completely FDD, right? What you have is small chunks of uplink, right? Where in the downlink form, and the G node B is actually doing uplink. I mean, it's receiving from one and then simultaneously transmitting to the other. Right? The key part of this is, in terms of resource allocation, this is not very different than, I mean, the overall resource is the same. The point is that in actual deployments, what you have is that most of the UEs are actually power limited. Right? So the power is asymmetrical. Right? The G node B is actually able to transmit much higher power on the downlink than the UE is actually able to transmit on uplink. So a lot of the capacity is actually limited by the power that the UE can transmit. So what can happen is that, if you're power limited, you can actually not be given a lot of resources, right? Because obviously you'll go below the noise floor. So what happens to these UEs is that you allocate very, very few resources such that all the power can be concentrated on those resources. Right? So this kind of allocation actually helps quite a bit, because what you can do is, you can see, right, in this case, the uplink, you typically have an ACK. When you send a downlink, you have an uplink ACK. Now, because there is an uplink opportunity available in every slot, right, you can, and this is a very small chunk here, the UE can actually transmit quite a bit of power, and every slot you have an uplink opportunity, right? So what this means is that you can actually reduce your latency quite a bit, right? So that's something that has been looked at, right? And obviously full duplex is as I said, this is the final aim where there are no constraints, right? Here, obviously you have constraints in terms of the UE still being half duplex, right? The UE is actually not doing simultaneous uplink and simultaneous transmit and receive. So just a quick this thing, right? This is a full duplex G node B that we had, right? Where we actually had the uplink array and the downlink array together, right? This is a macro cell with 1 kilometer coverage. So there was quite a bit of work done to establish 80 dB isolation between PX and RX, and the UEs were assumed to be half duplex, right? So the key message again here is that the subband full duplex can actually support simultaneous downlink and uplink for improved capacity and lower latency. The lower latency is the key part, right? You can actually, if you can get this cancellation, right? If the transmission is not, so for example, here the SNR you're showing, right? The SNR is actually not suffering. If you can design an array like this, where you are transmitting, receiving at the same time, at the same SNR, then this can be made possible. So how do you do this on the UE side now, right? So that's the next question. You can do it on the G node B side because it's a cost. I mean, the cost is not, power is not such a big concern. How do you do it on the UE side to make it full duplex? So that's the next avenue. Yeah, I think I don't know how much time do I have. I have 5 minutes. Okay. I had a couple of, I think sensing and other things we already talked about, so I'll probably skip that part here.
Thank you, Shri Agarwal, for this talk. So we have some time for the questions. If you have any questions, please ask.
Ashutosh, I have a few questions. One is, you spoke about terahertz. I see zero interest in terahertz when you go to these standardization meetings, right? Because of the way this millimeter wave has worked out, it has not been profitable. And what is Qualcomm's take on that?
Yeah, the idea, I mean, one thing has been that how much power are you going to consume, right? In terms of, so millimeter wave has, I mean, obviously North America there have been deployments, right? So the point that, I mean, whether the applications that we'll get, right, would be enough to consume that kind of data rate, that is one aspect, right? The other aspect is whether the overall, I mean, the profile of power, right, that you are going to get in terms of the device and the networks, right, is going to support that those kinds of terahertz or not, right? So that has typically millimeter wave has not been so successful primarily for these reasons, right? One is that we today don't have applications, right, which can consume, I mean, in most economies we don't have that kind of applications where those rates are required, and people are not really ready to pay that kind of money for it. So the idea is, will we actually get those rates? I mean, those applications, would people be ready to pay for it? Yeah, I mean, the point is, if it may happen, it may not happen. But what's the research angle? I mean, can we, from an engineering point of view, can we make it sustainable? So that's the take.
Okay. So second thing was you spoke about Giga MIMO. Then how much TX-RX chain Qualcomm is perceiving?
Yeah, so we are actually looking at least 128 right now. So we already have, as I said, 32. So we are perceiving to go at least all the way up to 128 ports.
128 TX-RX.
Yes.
Right, when you spoke about this access, what kind of new access schemes you are thinking about in terms of, you said the contention based.
Yeah, so
in terms of, I see in context of IoT, but in general it will be all slotted based for normal cellular access.
Yeah, so that's the problem, right? I mean, for example, I mean, again, right, technically speaking, what is happening is today, if you have slotted devices, right, and you're trying to cater to a lot of users, right, the problem is that you want the access to be such that only the user of interest typically wakes up, right? So what that means is just to be able to, I mean, you typically have PDCCH, right? I probably need to get a little bit more technical to that, about that. So you have a PDCCH, right, which tells every user whether in that slot it has something to look at or not. Now the problem is the whole idea of PDCCH or decoding the PDCCH is pretty power consuming, right? While if you go to WLAN, you have contention based, right? So the contention based mechanism is actually based on a preamble, right? So we have wake up receivers that we talk about, right, in cellular as well. The problem with that kind of approach is that if you want to wake up for a wake up receiver, or if you design a small sequence, right, it's actually not going to be able to support multiple users, right, a lot of users, which means if you send that, a lot of users would actually wake up, right? So that how do you bridge that trade-off, right? If you want to do, I mean, let's say you do multiple access within a particular bandwidth part, right? Design a bandwidth part which can serve only specific class of users and do contention based in that bandwidth part, right? So that kind of trade-off where you can optimize power for a certain kind of users by using contention based versus using larger devices which don't care so much about power, you do slotted based there, right? So that is what is being thought about.
Okay, so you said something about the propagation loss.
Yeah.
In the sub gigahertz bands, that is huge.
Yeah.
Is there any unique way Qualcomm is approaching to handle it, apart from increasing power and reducing the distance between hubs?
Yeah, so I think the primary thing would be, again, right, how do you, because once you go there, your wavelengths are going to reduce, right? So the primary focus or the primary thing that you would look at is beamforming, right? So how do you actually do and the key part there would be, if you don't have, I mean, if you have static users, right, beamforming becomes easier, right? Because your channel feedback is much better. You can do it over a long time, and you can actually support very, very fine beams. The challenge that we are trying to look at, right, is how do you do it for mobile users, right? So if you have a mobile user and you want to do beamforming for better beam gain, right, but the channel characteristics are changing so fast that by the time you actually receive the feedback, it's no longer valid, right? So that's another aspect where ML would probably come in, right, where you're actually able to predict, right? So I'll mention, right, I mean, you probably would have to run into ideas like digital twins, right? So what you would like to do is actually have a digital twin of the environment, right, where you're deployed, and then try to predict what the channel is going to be rather than actually measure it and then see. Once you have very good channel estimates, right, beamforming should actually get you where you want to be. The primary issue is with mobile devices where you don't really have very good channel estimates.
Okay, thank you.
So, similar to Rohit, building on this millimeter and terahertz, what kind of application Qualcomm is looking at, especially in those? Are there any?
Yeah, to be fair, right, I mean, Qualcomm doesn't look at applications.
I mean, but
yeah. So I said, right, in terahertz, right, one problem is actually going to be the RF design, right? So Qualcomm will be primarily focused a lot of focus would be how do you do this RF design to be able to fit in so many antennas, right? So many ports, while maintaining the power that we have, right? I mean, you could obviously build a large system, right, and demonstrate it. So we have some demonstrations, but they are very, very large systems, right? I mean, are you going to be able to put that on this size phone, right? Where would you put those antennas, right? Once you start putting those antennas, your correlations will start increasing, right? You may not get the same kind of diversity gains that you may expect. So how do you solve those kinds of problems? So those are the areas that may need to be looked at.
One quick question.
Yeah.
Good talk, Ashutosh. So my basic some technical question is 80 dB suppression or isolation for the full duplex you're talking about. So is it achieved using RF level or baseband level
It
together?
is both. It is both.
It is both.
It is both. Yes.
So do we have a split of in RF how much you do, in baseband how much you do, or?
Yeah, I'll need to check. Yeah, I can get back to you.
But the
exactly
80 dB is not RF alone.
Yeah, it's not RF alone.
It's
So
baseband
there is obviously a digital cancellation built in into this.
Thank you.
So I think I'll just add here that this cancellation is Professor Chaturvedi's student, Dinesh Baradia. So there is a lot to do. So everything is basically converging to Professor Chaturvedi. So thank you. I think those are mentioned in his paper. That is why I've seen those things. But thank you.
So let's thank the speaker once again.
Thank you.
And to thank him for coming here and giving this talk, I would like to invite Professor Chaturvedi to present him in Memento.